Cancer is the second leading cause of death worldwide, with 18 million new cases and 9.5 million deaths per year in 2018. For men, prostate cancer is the second most common cancer and fifth leading cause of cancer mortality worldwide, and the number of new cases and deaths is expected to increase by 2 by 2040. According to the World Health Organization, best treatment outcomes are obtained with early management of the tumors, which implies early detection and diagnosis of localized tumors, efficient local treatment. Brachytherapy consists of applying radiation directly inside the tumor, using tiny amounts of radiation sealed either in low-dose permanent seeds or temporary high-dose sources placed in straight needles. Brachytherapy alone or combined is of great interest to treat a tumor in its early stages, as it implies less side effects and risks compared to other techniques. Brachytherapy is commonly used in gynecological, prostate, and breast cancers as monotherapy, or as a boost for external beam therapy. For treatment of prostate tumor, brachytherapy provides excellent clinical outcome with a short treatment and hospital stay, and reduces sexual and urinary functions impairment observed with other therapies. Using ultrasound guidance and a placement grid to control the needle's insertion, brachytherapy requires long training and skilled practitioners to be the most effective.
My name is Roshdi Nazuki. I'm from University of Lille. With our team, we are managing the CoBra project developed in the framework of Interreg 2Cs. This project aims to improve localized tumor diagnosis and treatment thanks to MRI real-time guided robotics solution for biopsy and brachytherapy. The localization we are working on is our prostate and hand and neck, and the aim here of this collaborative project is to interoperate between various competences from the region of 2Cs in the field of dosimetry, in the field of imaging, robotics, needle design for diagnosis and treatment of localized cancers.
The CoBra project is possible thanks to the cross-border collaboration of 9 partner organizations from France, the UK, Belgium, and the Netherlands, with the support of the European Regional Development Fund. CoBra partners have developed 6 modules: real-time MRI-based calculation of radiation dose, steerable needle trajectory optimization, active steerable needle system, automatic biopsy system, MRI-compatible integrated robot solution, innovative phantom for practitioners training.
Kevin Bourbonnier, a final-year PhD candidate under the supervision of Nick Reinhardt, a medical physicist, and David Pasquier, a radiation oncologist. The goal of the CoBra project is to build a brachytherapy device under MRI guidance. This implies numerous challenges, and here in Oscar Lamboli Center, we are working on 2 aspects. On one hand, a solution robust to MR intensity variability, since every MR acquisition can be different according to machine constructor, sequence, and acquisition parameter. On the second hand, the use of this device in real time. The first issue is partially solved by transforming the MR image into a synthetic CT in order to predict a Monte Carlo dose distribution. Deep learning, with the help of generative adversarial network, are used here to provide a fast and accurate answer.
Our team consists of Dylan Jones, Professor of Mathematics, Dr. Sina Fairouzi, Research Associate, and myself, Ashraf Labib, Professor of Operations and Decision Analysis at the University of Portsmouth, UK. Based on the steerable needle, our task at the University of Portsmouth team is to develop a trajectory planning and optimization algorithm of the path of this needle.
The algorithm receives a seed distribution plan as an input, which is developed by our partner Oscar Lambert Center in Lille, France. After that, the algorithm develops trajectories for the needle to cover all seed positions. The trajectories are based on the needle design developed at the University of Delft, our other partner. The trajectories are optimized to avoid organs at risk and also to minimize tissue damage.
Hello, my name is Sean van der Dobbelsteen. I'm an associate professor at the Department of Biomechanical Engineering in Delft University of Technology.
And my name is Martijn de Vries and I'm a PhD researcher.
Within our department we mainly focus on the development of novel medical instruments for minimally invasive therapies.
And within my research I'm focusing on the development of a novel steerable needle design to optimize LDR brachytherapy interventions. Steerable needle should allow for 1. Better control of the needle track and end location during needle placement, and 2. Allow for an enlarged reach within the prostate for a more homogeneous dose distribution.
Needle tip steering up to 50 mm can be achieved by the use of a flexible mechanism integrated in the needle system. Linear movements of the motors on the proximal end allows for steering at the distal end of the system, as we can see in the video.
Here you can see steering of the needle when puncturing a gelatin phantom as well.
Hello, my name is Pieter Wiskerke. I'm a project manager for the DEMCON part on the CoBra project. DEMCON is a large engineering company in the Netherlands, specialized in medical devices. And in the CoBra project we are responsible for the biopsy module, which is used to take the biopsy from the prostate.
My name is Helene Kalkoen. I've been working as a system engineer on the development of the biopsy module by DEMCON for the CoBra project. For this we had to look into finding the right requirements to build an MRI safe system, mainly oriented to selecting the right actuators and sensors, as well as material choice. Furthermore, we put a lot of effort in getting the accurate biopsy quality, so defining the speeds we would need for firing the needle.
Hello, my name is Thomas Eisma, mechanical engineer at DEMCON. Within the CoBra project I was responsible for the mechanical design of the biopsy module. The main challenge was to design a fully functional model within the limited volume in the MRI scanner. As it will be used in an MRI scanner, we have used a limited volume of metals, and we looked mainly at plastics and ceramics.
Robot Guide is the main component of 3 Tesla MRI-based robot for brachytherapy, designed and developed in the framework of the CoBra project. It is composed of a parallel robot mechanism sized to cover a 3D workspace of prostate organ area accessible from a lithotomy position of the patient. The Robot Guide is a 5 degree of freedom robot motorized by a piezoelectric motors. It can be controlled in closed loop, jointly in position and velocity. This is due to the presence of encoders and absolute sensors for their joints and links operated in high fields of MRI. The Robot Guide can adapt its trajectory through its global control from the MRI analyzed data. When the biological data change, it shapes during invasive operations. The robot is used to guide 2 types of nodules: biopsy model that can be used to extract biological tissue from location targeted under MRI, and low-dose radiation brachytherapy model used for localized treatment with radioactive seeds accurate deposit.
Hello, I'm Sarah Wilby, a clinical scientist and PhD student working on the CoBra project alongside my colleagues and supervisors at the Portsmouth Hospitals University NHS Trust, Wojciech Polak and Tony Farmer.
Our goal is to develop a pelvic phantom that can be used to confirm the accuracy and reproducibility of the CoBra robot in the environment that replicates the clinical scenario as closely as possible. Furthermore, this can be used as a training tool for practitioners.
The key challenge here is to combine realistic mechanical properties of needle-tissue interactions with materials that produce suitable imaging characteristics in MRI and allow for integrated dosimetry. The images here show some of the development steps to date.
For training purposes, the CoBra projects are taking two approaches. While our remit is to develop a physical phantom, our colleagues in the University of Lille are focusing on a virtual one.
In this work package, we are working on a simulation for training people on the system, but also to evaluate the robotized procedure. The geometry of models are originally obtained with the MRI. Then we can simulate the behavior of the tissue. In particular, the interaction with the needle. We can afterward deform the MRI so that the image follows the deformation of the tissue.
With automated real-time MRI-guided robotic biopsy and brachytherapy procedures, CoBra technologies will allow better tumor diagnosis and higher chance of survival for patients. New therapeutic option for localized tumors with high efficiency, reduced side effects, and better long-term quality of life.